Now we're going to get into area, and in the next section we're going to see how does area and what we just did with anti-differentiation connect. But before we can do that, we've got to discuss some new terminology which you may or may not have seen in pre-calculus. So we want to go over kind of what summation notation is. So if we think about the sum of n terms, so if I'm taking a1 plus a2 plus a3 all the way up to an, this is written as, you could write it out with a plus in between each and every term. And these dot dot dots basically meaning all of the same pattern happens in between. But realistically, we want to write this in a much cleaner, concise way. And so what I'm going to do, if you notice, this constant is what's changing every single time. So I'm going to call that AI. And it's basically going to be a function that I'm going to plug values of I in for. You're going to start with I equals 1 because the very first value we have here is A1. And we're going to stop when we plug in n. So my upper bound will be n. And what I'm going to indicate to say that I'm going to add things over and over is the Greek letter sigma. So we can write this sum in very concise notation called sigma notation. And so all of these pieces have names. I is our index of summation, so it's the thing that's going to be changing. AI is the ith term of the sum, so it's what you get when you plug in I equals 5 equals 6 equals 7. N is the upper bound, 1 is the lower bound, and sigma is really a Greek letter, so indicating a sum. Okay. So before we see the connection with area and this summation notation, we're going to get a little bit of practice just evaluating sums. So we want to be comfortable kind of understanding what these mean. And so you see we have an expression that's on the inside. This is what we're plugging these values of I in for. And what we're going to do is we're going to start with I equals 1, and we're going to stop when we plug in 4. And we're just going to increase by 1 every single time. So I'm going to plug in I equals 1 first, then I equals 2, I equals 3, and I equals 4 into this expression. So when we plug in I equals 1, that would be 9 times 1 plus 2. We're going to add to that, plugging in I equals 2, which would be 9 times 2 plus 2. Add in, plugging in I equals 3. Add in, plugging I equals 4. And so really you see we end up with just numbers, which we can then condense. So 9 times 1 is just 9. 9 times 2 is 18. 9 times 3 is 27. And 9 times 4 is 36. So I'm going to take my first term, A1, is 11. My second term, A2, is 20. My third term is 27 plus 2, so it's 29. And my fourth term, corresponding to I equals 4, is 38. So if I add all of these together, I end up with 98. Okay. Now, you don't have to start at 1. You can start the index at something different, and that's perfectly okay. When we talk about the area, we're going to be starting at I equals 1. And you can change that summation letter as well. It's just indicating J is the thing that's going to be changing. So what we're going to do to evaluate this sum is we plug in J equals 6, increase it by 1 to 7, 8, and we stop when we get to 9. So we're going to plug these values of J into this expression. So that would be 1 over 6. Plug in 7 gives you 1 over 7. Add plugging in 8. Add plugging in 9. And then you can plug this into a calculator. You'll get a nice decimal form, which isn't that nice because it's a big number. It's 274 over 504. But if you do actually evaluate that, it's roughly 0.5456. Let's try one last one before we start working with some properties of summations. We want to use sigma notation to write this sum. And so what we kind of have to notice is what is changing in this expression, and also what do I start at, what do I end at. So I know I'm going to write this with a sigma, but how? If you consider this, the 1 stays the same every single time. Also, 7 stays the same every single time. So I'm going to keep that 1 over 7. That does not change. What does change is this thing that it's being multiplied. So it's getting bumped up by 1 each and every time. That's the only thing that changes, and it goes up by 1. I'm going to start this thing at 1, and I'm going to end it at 42, because the last value I'm going to plug in is 42. So this tells me all of my missing pieces of information. What I need down here is I need just an expression, I. So in the denominator, I get I, because that's going to change. I'm going to start by plugging in I equals 1, and I'm going to stop when I get to 42. So now that we've got a little bit of a better hand working with the sigma notation, we're going to go over some summation formulas and properties. Some of them I unfortunately don't have time to actually show you. If you do remember going over induction in pre-calculus, you probably did some of these formulas or showed that some of them were true. So you can look it up if you need to, or you can just kind of accept my word for it, up to you. The first couple are going to be straightforward. It's the last 3 that aren't as clear-cut as to why. But first, if I have a constant times this thing that's changing, so A is changing A. So first, if I have a constant times this AI, so AI, remember, is the thing that we're going to plug I into. It's changing every single time. That constant really does nothing. Every single term has that constant attached. So really, you can just pop the constant out of the entire sum. So it only works when K is a constant. If I want to add 2 things that both deal with this variable I, you can really just take the summation of each of them individually. Likewise, if I'm subtracting 2 things, I can take the sum of their subtraction. Okay? If I want to add up a constant C n times, this is basically C plus C plus C plus C plus C, because there is no I in here at all. What you're going to do is start at 1 and end at n, so you're really adding this up n times. So I'm taking C, adding it up n times, you're just going to get C times n, where C is a constant. So if I'm adding up 5 and I'm doing that 10 times, I'm going to get 50 as that sum. Okay. Now these last 3 are the ones that you kind of have to accept my word on, or again, you might have seen them when you did induction, if you did that in your pre-calc class. If I add up I from 1 to n, so that basically means 1 plus 2 plus 3 plus 4 plus 5 all the way up to n, this will equal this end value n times n plus 1 divided by 2. So we'll get some practice with these so you can kind of see what we mean. But if I'm summing up 1 plus 2 plus 3 plus 4 plus 5, my n index would be 5. It would be 5 times 5 plus 1 divided by 2. That's what the sum would equal. If I want to add up I squared, so 1 squared plus 2 squared plus 3 squared plus 4 squared, that's a little more complicated. It would end up equaling n, so again, that upper sum, n times n plus 1 times 2n plus 1 over 6. And likewise, if I want to add up I cubed from 1 to n, it would be n squared times n plus 1 squared over 4. And the key about these is to use these formulas, all of these indexes must start at 1. If I go 3 to 100, I can't quite use this formula. Okay. So again, you can look up actual proofs of those, but it does require induction. You can try it out with some smaller values if you want to get a hang of it, but these are formulas that we are going to use pretty frequently. So let's try some practice. Let's go ahead and evaluate the sum, and we're going to go from 1 to 24 of 3i. So I want to use my properties to my advantage. That 3 is a constant, so it pops out, and I'm left with the sum of 1 to 24 of I. Going back and utilizing this formula, that will equal 3. I get my upper sum, which is 24, times 24 plus 1 divided by 2. So that's really 3 times 24 times 25 over 2. And so basically, if I add up 3 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5, all the way up to 3 times 24, I'm going to end up with 900. Okay. Let's try another one. Let's add up from 1 to 15 of I minus 1 squared. Right now, that's not any of the formulas I know. So what I want to do is go ahead and FOIL that. So it's still the sum from 1 to 15. If I do I minus 1 times I minus 1, that's I squared minus 2I plus 1. And then for each of these, I can take the sum individually. So it's the sum of I squared. I can pop the 2 out and I subtract. So I get minus 2, sum of I, plus the sum of 1. And all of those start at 1 and go to 15. Okay? So for I squared, we go ahead and utilize this formula. That upper index is 15. So pretty much on this left-hand side, I'm going to plug in 15 for n. So that's going to equal n times n plus 1 times 2n plus 1 over 6. And then for I, I'm again going to use this formula with n being 15, but I do have that minus 2 out front. So I get n times n plus 1 over 2. And then the last one, I'm summing up 1 from 1 to 15. So that's 1 plus 1 plus 1 plus 1, 15 times. My last summation is 1 times 15. Okay. Now it's just a matter of simplifying. So if you go ahead and do all of that multiplication and addition, 15 plus 1 is 16. 2 times 15 plus 1 is 32. Over here, these 2's end up canceling, so that's nice. So you really get 15 times 16 plus 15. And again, if you simplify this, you should see that when I sum up these terms, I'll end up with 1,015. Now we're going to see how this summation and how some of these formulas ultimately apply to areas. And what we're going to do is begin by attempting to solve the area problem. And that's, we want to find the area of a region S, which is under the curve of some function from A to B. So kind of thinking about this graphically, you have some function which has some funky shapes to it. You want the area under this function from x equals A to x equals B. If I had a nice shape, so suppose I had straight sides like triangles, rectangles, we could definitely do that. But if I give you like the curve y equals x squared, y equals x to the third, the cosine function, I don't have nice geometric formulas I can use. So instead, remember this process we're going to do is we're going to approximate the area with rectangles because we know how to find the area of a rectangle. Then I'm going to let the number of rectangles I take approach infinity. So we're going to bump up the number. And so what I'm going to do is kind of walk through a example of what we mean by this approximation process. It's going to introduce all the notation we need that you're going to see within your homework, and we're going to see how it in turn leads to a better and better and better approximation. And we're going to work exactly with this function y equals x squared. We want the area under this parabola from 0 to 1. Okay? So first and foremost, we can graph our parabola function. What I want to do is I want to find the area from 0 to 1. So ultimately, I am looking for this area in here. I'm not going to be able to color it in too perfectly, but that's okay. This is my goal. Find the area of this region S. If I want to consider the simplest approximation, well, if I go ahead and draw a box around this, I definitely can say it's within this box that has height and width 1. So the area is going to be less than 1. And it's also definitely positive. So ultimately the area must be some number between 0 and 1 since it's in the square of length 1. But this is a really, really, really bad approximation. As you can see, 1 has all this extra space up here, which isn't very good. And I know I don't have 0 area, so not so great. What we're going to do now instead is I'm going to take this same shape and I'm going to divide up how many strips I use to approximate. So what I'm going to do is instead divide this region S into 4 strips. So we're still looking for this exact same area. So let's go ahead and shade it in so we know what we're searching for. And I'm going to break this up into 4 strips that all have equal width. And I'm going to approximate the area in 2 different ways. Okay. So by breaking this, I want to cut it in half. So that would be at 1/2. And then I want to cut each of these in half again. Okay. And that creates 4 strips, 1, 2, 3, 4. Each of which I'm going to approximate the area on. Okay. So each rectangle has exactly the same width. And if I want to figure out the height, I can really use one of these endpoints. So say on this first interval here, I can go ahead and use this y value to get an approximation for my height. And that will be an over approximation because it's slightly over, but that's okay. Then on the second strip, I can use the right endpoint again to get the height. And it will again give me something that's slightly over, but that's okay. I'll use the right endpoint over here to get my height, right endpoint over here to get my height. And on each of these, I can find what my area is roughly equal to. Still not perfect because you can see I'm going over top my function and I've got all this extra space. So it's going to be an over approximation, but that's okay. It's still better than saying 1. Okay. So to find each of these heights, we'll start over here because this one's a little easier to write in. The height here would be the function evaluated at 1. This is 3/4 because that's exactly halfway in between 1/2 and 1. And so the height of this other rectangle would be my function evaluated at 3/4. This height would be my function evaluated at 1/2. And this height would be my function evaluated at 1/4. Okay. So I'm using the right endpoint of each subinterval, which is from 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and 1/4 to 3. So I'm plugging each of these into this function to find the height of the rectangle. Because this entire region has a length of 1, and I'm using 4 subintervals, every rectangle has width 1/4. And the heights would be, we plug in 1/4 into the function, so that's 1/4 squared. If we plug in 1/2, it's 1/2 squared. 3/4 is 3/4 squared. And 1 is going to be 1 squared. So the notation we're going to use to indicate that I used a right endpoint with 4 subintervals is going to be R4. And so ultimately, my approximation then is my width of my first rectangle, which is 1/4, times the height, which is my function evaluated at 1/4. Moving on to this next interval here, that width is 1/4 as well, and the height is 1/2 squared. My third strip has 1/4 as its width, the height is 3/4 squared, and my last rectangle has width 1/4 and height 1 squared. So plugging all this into a calculator, the area of these 4 rectangles is about 0.46875, okay? And again, this is going to be an over approximation. So ultimately, my true area is smaller than this. But that's still way better than saying my area is definitely less than 1. Okay? Now we can do the same thing, but let's try using the left endpoints to approximate the area. So we're going to draw another picture, fill everything in, and try to go through it not too quickly. Okay. So I still want to break this into 4 equal strips. So I cut it in half to give us 1/2. Cut it in half again, gives us 3/4 is that point. Cut it in half again, gives us 1/4. And so I'm going to use the left endpoint to find my areas. So on this strip here, I'm going to plug in 3/4 to get my height. And so you can see this will now be an under approximation because I've got a lot of missing space up here. Okay. On this strip, I'm going to plug in the left endpoint, which is 1/2. So I'd plug that into my function to get my height of this rectangle, which again is an under approximation. On this strip, I'd plug in 1/4 to get my height. And then when we move to this final one, I plug in 0 to get my height, so I really just get nothing on that. So we'll call this strip 1, strip 2, strip 3, strip 4. Okay. So the sum of these rectangles, we're going to use L4 to indicate it's the left end point. My first strip, which is 1, has width 1/4, and its height is my function evaluated at 0 because I'm using the left end point of that interval. To do our second strip, the width is still 1/4, and I'm using the left end point, so I'm plugging 1/4 into the function. For the third strip, my width is still 1/4, but on this third one, I use the left end point, so I plug in 1/2. And on our final piece, our width is 1/4, and our height is still going to be plugging in the left end point, which is 3/4. Okay. So evaluating our function at the left end points would give us 1/4 times 0 squared, 1/4 times 1/4 squared, 1/4 times 1/2 squared, 1/4 times 3/4 squared. And so you can plug that into your calculator to see this would be 0.22 roughly. And again, you can see now this is an under approximation because I've got this gap between my rectangles and my true area. So it's an under approximation, so my area is definitely bigger than this 0.21875, but I also know it's smaller than 0.46875. Okay? You can really keep doing this process as much as you want. The more strips you take, the better, because you're going to have less of a gap or less of a gap underneath as well. So to kind of give you 2 examples, you can go through the same exact process, but I'm going to, for time's sake, just kind of quick draw it. So it would take me long amounts of times to do that. Okay. If we split this up into 8 subintervals, so I cut it in half, cut it in half again, cut it in half again, and then cut each of these into smaller strips as well. Okay. And then did the same thing over here. Cut in half, cut this section in half, half, and then everything in half again. So we have 8 strips we're going to do approximations on. On the left, on this strip, if we want to do an over approximation using those right endpoints, we would go a little bit over. We would use this point, and then we'd get this over approximation. Okay. And if you do that using the right endpoints, you'd see it would be about 0.39. If we use the left endpoints, again, you're going to get an under approximation because it's going to be below the curve. So under, 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 and then the last one, not going to have anything there. But if you use the left endpoints, you'd see it's about 0.27. So again, your area is going to be trapped between these two numbers. And you could keep doing this process over and over. If you did 1,000 strips, your area would be trapped between these two quantities. So ultimately, a good estimate is probably around 0.333335. And this is going to be where a true definition of area comes into play. So we're going to deal with the area under a function, and we're going to divide this region S that I want to find into n equal strips of all equal width. So I want to find the area under the function f over this interval from a to b. And so I'm going to approximate the area on these n arbitrary strips. So you can see where summation is going to play because I'm going to sum up these areas. If I want to know what this width is of each and every single strip, we know the length of the interval is b minus a. So if I want the width, I'm going to take the length of my interval divided by the number of strips I want. So every single strip is going to have width b minus a over n. It's a fixed number. In the last example, when we had 4 intervals that we split it into, each and every strip was width 1/4. So this is a constant that we're going to call delta x. It is our change in x. So every single one of these has width delta x. It doesn't matter which interval you were on, it's width delta x. To find the height, we can use those right endpoints again. So this is going to be our first right endpoint, our second, our third, and that process is going to keep going. That's the ice strip, so this would be the ith endpoint, and then it's going to end at B. Okay. So ultimately, the strips divide A minus B into n subintervals. You start at really A and end at x1, then start at x1, go to x2. You keep doing this process until you get to that last strip and you end at B. And what I need to do is plug the right endpoints into my function to get my height on all of these subintervals. So I want to come up with how can I express the right endpoint, okay? So let's think about this first endpoint, x1. What we do is we're starting at A and we're adding this with delta x. So I add delta x to it. To get x2, I start at x1 and again I add that with delta x. So this is equal to x1 plus delta x. Your third would be x2 plus delta x. Okay. But really I know what x1 is in terms of my starting point and this quantity delta x. So I can go ahead and replace that. That's a plus delta x plus another one. So really for my second right endpoint, I take my initial point and I add 2 of these strips. If I want my third, I take my initial point and I'm adding 3 of the strips. So in general, if you want the ice strip or my general term, I've added I delta x's to my starting point. So ultimately, I'm going to plug this into my function to get my height. So we can approximate the ice strip by a rectangle with width delta x and height, my function evaluated at xi, which is basically just the function evaluated at the right endpoint. So the area of my rectangle is my height times width. So that area is my function evaluated at the right endpoint times delta x. And adding these together gives us an approximation to the area. So my area is about equal to adding up these rectangles using the right endpoint. This is my function at the first right endpoint times delta x, my function evaluated at the second times delta x, and I keep going until I get to that last strip with height f evaluated at the right endpoint times delta x. And then if you take more and more strips, you get a better and better approximation, okay? So this leads to our formal definition of area. The area A of the region S that lies under the graph of a continuous function is the limit of the sum of the approximating rectangles. So what that means is we're letting the number of rectangles we take approach infinity. So I'm letting this number of rectangles approach infinity. So my true area is the limit as n goes to infinity of Rn. Okay? And so really, I'm adding up all of those rectangles and I'm letting that number of rectangles go to infinity. And this inside can be condensed much nicer using that summation notation. So it's the limit as n goes to infinity, and I'm basically changing this right endpoint every time. So I'm starting this index at 1 and ending at n. And my delta x is going to stay the same over and over and over. Okay? Now realistically, this is saying using the right endpoint, but you can use the left endpoint to get the same thing. Because when you're taking so many strips, there's not going to be room for error. So it really doesn't matter which endpoint you use. And in fact, you really can use any number inside that subinterval. So we let this xi star represent any point inside the ice subinterval to be used to find the height of the rectangle. And these numbers are basically called sample points. So if I want to approximate this function with 4 subintervals, I can pick any point I want on each of these subintervals to find my height. Like I could pick this as my x1 star, and I would use this y value to give me the height of my rectangle. My width would still be that same delta x, which is the same for each strip. So I can use this as my approximating point. I could pick something over here, closer to this endpoint, to get my sample point on my second interval. And so this would be what we use for our height. And we go ahead and find the area of this rectangle using our approximation. I can pick an endpoint itself. So I can pick the right endpoint on the third strip to get that approximation. And that's okay. It is a sample. And then finally, I could pick that same endpoint to get my height over here. So I can make x3 and x4 star exactly the same. Because when you have an infinite number of rectangles, it doesn't matter what you pick from inside there because you're going to have such smaller and smaller and smaller strips. Okay. With this idea, because you do get the freedom to kind of pick, we have something called our lower and upper sums, which basically indicate which point you pick to give you an over or under approximation. So we can form lower sums or vice versa upper by choosing sample points, which are xi star, so that this point, when you plug it in, gives you the smallest y value possible on that interval, or likewise a maximum. Really, that definition is kind of a little bit confusing. I get it. So instead, let's go ahead and look at it with a picture. If I have this function from a to b, I want to pick the point that gives me the most for my maximum. So on this first strip, if I want to make my height as large as possible, I would pick this point to give me this over approximation as big as I possibly can. On the second strip, This is the largest y value I have, so I would pick that point to give me my upper sum. On this strip, I'm going to pick this same point again because that's the tallest that this thing possibly is. And on my final strip, I would pick the left end point because that will give me my over approximation on that interval. So the pink ones give us the upper sum. If you want to go to the lower sum on this interval, I would pick the left end point to make my height as small as possible. This interval, again, the left end point to make my height as small as possible. Now I'm going to pick the right end point to make my height as small as possible. And again, on this last interval, I'm going to pick this right end point to make my height as small as I possibly can. So let's try one last example. We're going to use the upper and lower sums to approximate the area of the region using the given number of subintervals of equal width. So the function we're dealing with is the square root of 1 minus x squared. We're going to do 5 subintervals over the interval from 0 to 4. Okay. So that interval is length 1. I need 5 subintervals. Each strip is going to have length 1/5. So my delta x is going to be the length of the interval divided by 5, which is 1 over 5. Okay. So using our picture, this delta x is the width of each of these strips. And if we fill in the pieces, this first one is 1/5. If I add a fifth to this endpoint would be 2/5, 3/5, 4/5, and then we end at 1. Okay. So on each of these subintervals, I want to figure out what point do I pick to maximize it or minimize it. Okay. So we're going to start with the upper sum. And again, going to utilize that same picture. So what I want to do is on this first strip, the point that's going to give me the largest height is the left end point, which is 0. Okay. So I'm going to use 0 to get my height of this strip. So we're going to keep a running tally. We're going to call this S5 to mean the upper sum with 5 strips, so capital S. Okay. On the first strip, our height is f of 0, the width is delta x. Moving on to this second strip, I'm going to use the left end point again, which is 1/5, to get the height of my rectangle. And so I'll plug 1/5 into my function, and I want to times that by delta x to get the width. On the third strip, I use the 2/5, plug that into my function to find my height, and then the width is delta x. On this fourth strip, the left end point again is the one that happens to work for us to give us that biggest approximation. So I'll plug in 3/5 and then times that by delta x. And finally, on the last strip, we use the left end point again to do this over approximation. So I'm going to plug in 4/5 and times it by delta x. So all of these values I want to plug into this function, square root of 1 minus x squared. And so if you go through and do that, when you plug in 0, it'll be square root of 1, and then we'll times it by 1/5. If you plug in 1/5, it'll be 1 minus 1 over 5 squared. So you're going to get square root of 24 over 5, and then times 1/5. If you plug 2/5 in, you'll get root 21 over 5 times the 5th. 3/5 will give you root 16 over 5 times the 5th. And then 4/5 will give you root 9 over 5 times 1/5. So plugging that into a calculator, you're going to get that this area is approximately 0.859. Okay. So let's try the same thing now, but let's do the lower sum. And what we're going to do is use a lower s to indicate this is a lower sum. The 5 on the inside is indicating we're using 5 strips. So same picture, but now I want to go through and I want to figure out which point do I use to get my lower estimate. So for this first interval, if I'm picking a point along here, because it is decreasing again, I'm going to now pick the right endpoint. So we get this as our height. So I'm going to plug in 1/5 times it by delta x to get my approximation. On the second strip, I'm going to plug in 2/5 because that's the lowest value. So we'll plug that into a function, times it by delta x. On the third strip, you will plug in 3/5 to give us the area of the third strip roughly. Fourth strip again, plug in the right endpoint, which is 4/5. So you get 4/5 times delta x. And then if you want to go ahead and do this last one, the lowest strip you can get is going to have width 0 because you'll plug in 1 to give you a height of 0. And so again, you plug this into the square root of 1 minus x squared and then go through that process for all of them. And if you plug it into your calculator, you're going to see this is about 0.659.